Welcome. In this session, we'll explore a constraint optimization problem from a previous session. The problem that we'll explore here is it'll be a first function that has a vector argument of size 2, and that objective is the squared norm of the argument. And we'll apply a first constraint, so we'll call that one form 1 times the argument minus the first constraint constant, and we'll say that that has to equal 0. So we want that to apply at always. Specifically, we want that to apply at the minimizer. And if we write this in our standard form, we see that it should be 1/2 times W transpose KW, and that implies that our K, which is missing from this formula, actually is 2 times the identity. And we'll say that the constraint 1 form here is the difference between the entries of the argument, and we'll say that the constraint constant here is -3. So this is what we had previously. To solve this, we'll go through our algorithm. So step 1, what we do is we compute the B matrix. Now, because this is just a scalar problem, this is going to be fairly simple, but B will equal, we'll take the constraint 1 form, multiply it by the inverse of the symmetric positive definite matrix, and multiply that by the transpose of the constraint 1 form. So in our case, that is -1, 1 times the inverse of 2 times the identity is 1/2 of the identity, and then we transpose that so that we get the vector -1, 1. And when we go through this, the first entry will be -1 times 1/2 times -1 is 1/2, plus 1 times 1/2 times 1 is 1/2. So that will equal 1. So not the identity, it'll equal 1. Step 2 is we simply say that our solution vector is our constraint vector, and in that case, so we'll simply write that constant, that scalar, is in this case -3. Step 3 of our algorithm is we solve. What we want to do is we want to take the partial derivative of the Lagrange dual with respect to, in general, the Lagrange multiplier vector, and we want to transpose that and set that equal to 0. So in our case, this term, the partial derivative of the dual with respect to, now it's just a scalar, and that'll be a scalar, but we'll keep the transposing. So that will equal minus our B matrix times our Lagrange multiplier minus S. And when we set that equal to 0, that's equivalent to saying, and solve for the specific Lagrange multiplier, if I take this over to the left-hand side, that will be B times our optimal Lagrange multiplier equals minus S, or we could write that as the optimal multiplier equals minus B inverse times S. So this is a general solution, and in our particular case, B is 1, so B inverse is 1, so that will be -1, well, let's write that, even though the 1 over 1 is 1, we'll keep that formalization, and then here we have -3. And we can see that those will cancel out, 1 to the minus 1 is 1, so that means our optimal Lagrange multiplier for this problem is 3. And then in step 4, we compute, from this, we compute the minimizer of our constraint problem. So in general, this is that any vector, any argument vector, can be represented as minus the symmetric positive definite matrix inverted times the transpose of our constraints times the Lagrange multipliers that we found. In our specific case, the optimal vector is minus 1/2 times the identity, so that's the inverse of our symmetric positive definite matrix, times the constraint transposed, which is minus 1, 1, times our optimal Lagrange multiplier. And that is 3, so that is minus 1/2 times minus 1, so that's 1/2 times mu, is 1.5, and this is minus 1/2 times 1 times 3 is minus 1.5. So now let's check with our previous results. Previously, we had the enlarged matrix, the augmented matrix, was we put K in the upper left, so that would be 2, 0, 0, 2. We put the constraint 1 form as this row, so that would be minus 1, 1. We transpose this to be the vector minus 1, 1. We always put a 0 in that lower right corner, and that would be times the optimal vector and the optimal multiplier, and our constraint was that that had to equal 0, 0, minus 3. And we can verify just by a simple matrix vector multiplication that if we take this matrix and we multiply it by this vector with the 3 augmented for the Lagrange multiplier, that we get the solution matrix. So what we've done is we've solved the same problem, but by using the dual formulation, what we've done is we've solved a smaller problem first and then solved the primal problem.